Some problems in life are just too big to solve. Recursion makes big problems small problems. Let's explore its power. Let's start off with a simple example. Jeff is climbing up a 7-stair staircase. Jeff can climb 1 or 2 stairs at a time on every step, but he's allowed to climb on the last step 3 stairs. This should say Jeff. And how many distinct ways can he get to the top? So there's 7 steps or 7 stairs, and he's starting on the bottom stair or the ground floor. And this is step 1, step 2, 3, 4, 5, 6, and 7. And essentially, he can climb 1 or 2 steps. Okay, so this would be a very hard problem to do casework with. There'd be a bunch of cases. 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 2, 1, 1, 1. Okay, that just seems way too out of hand. Casework is not going to be easy. Not at all. So instead, we're going to use a very cool technique called recursion. Let's explore. So this problem 7 is a decently big number. I mean, it would be pretty easy to solve if it was just 1 or 2, right? After all, that would just be one case. Okay, so how many ways to get to the first step? Let's say it was just a 1-step staircase. He can climb 1 or 2 stairs at a time. So how many ways are there to go from the 0th step to the first step? That is 1 way. That's it. Just 1 way, because Jeff can climb 1 or 2 stairs, so there's just 1 way because you climb 1 stair. Now, what about to go from the 0th to 2nd stair? How many ways are there to do that? Well, you can either take 2 1-steps, right? So we can take 2 steps, 2 single steps, or we can jump both stairs in 1 single step. 2 ways, right? 2 ways. And we can keep going on and on. Let's try one more to go to the 3rd step. How many ways to go to the 3rd step? So this is a little bit more. You can take 3 steps that are 1 each. So you could just go 1 at a time, nice and slow. You could have the first step could be 2 and then 1. Or you could have the first step being 1 and then 2. So in this case, we've got 3 ways. 3. Cool. And beyond this, it's going to become way too hard to casework. So the idea behind recursion is you find the number of ways to go to the 4th step in terms of the previous values. How might we do that? So here's the thing. To go to the 4th step, we either must take 1 stair from the 3rd step. So to reach the 4th step, reach the 4th stair, Jeff starts at the 3rd stair and takes 1 step. That's 1 way. So let's write that. Reach the 4th stair. You can be on the 3rd stair plus 1 stair climb. Or you can be on the 2nd stair and a 2-stair climb. Right? Because if you're on the 2nd step, you need 2 to get to 4. And these are really the only 2 ways to reach the 4th stair. 3rd stair, 2nd stair. We already know the number of ways to reach the 3rd stair. And we also already know the number of ways to reach the 2nd stair. Could we maybe write an expression in terms of the 2nd and 3rd stairs? Indeed, we can. So the idea here is, let's say f of n, it's a function, f of n is the number of ways to reach nth step. Cool. F of n number of ways to reach the nth step. So we already know that f of 1 is 1, right, from here. F of 2 is 2. F of 3 is 3, right? We just discovered that. F of 4, well, we don't know that yet, but we came up with these two cases, right? So f of 4, how many ways are there to reach the third stair? There's 3 ways, or let's just say f of 3 for now. So there's f of 3 ways to reach the third stair. Maybe I should write stair just to be clear here instead of step. So f of 3 ways to reach the third stair, and how many ways just to take a 1 stair hop? If you're on the third step, how many ways just to go 1 step up? That's just one way, right? There's only one way you can go 1 step up. It's just one jump. Similarly, on the second stair, there's f of 2 ways to reach the second stair, and then also there's only one way to take a 2-stair jump. Let's just write that here. 2-stair jump and 1-stair jump, let's say. There's only one way to take a 2-stair jump. You just go up by 2. That's it. We're not saying 2 1-stair jumps, just one single 2-stair jump. That's just one way. So f of 4 is just f of 3 plus f of 2. Aha! We know f of 3. We know f of 2. F of 3 plus f of 2. 3 plus 2. 5. So f of 4 is 5. Let's see if we can do something similar. Or let's try and find the general formula. So let's say the nth stair, f of n. What is this going to be equal to? So to get from the nth step, we can either go to the n minus first step, so f of n minus 1, and then take a one step hop or 1-step jump, or go to the n minus second step and take a 2-step hop or jump, whatever. And like we mentioned earlier, there's only one way to take a 2-step jump. So we have what we call a recursive equation. Yes, that's where the recursion name comes from. F of n equals f of n minus 1 plus f of n minus 2. And we already used this here. F of 4 is f of 3 plus f of 2, right? Now f of 5 equal to f of 4 plus f of 3, right? That's 5 plus 3, 8. F of 6 is f of 5 plus f of 4, right? What we're doing is we're just plugging it in over here, right? F of 5 plus f of 4, and that's 8 plus 5, which is 13. Now f of 7, here's where we have to be careful, because the problem says on the last step, he's allowed to climb 3 stairs. So for most of the journey, Jeff can only climb 1 or 2 stairs at a time. But on the very last step, so if he's about to reach the 7th stair, then he can take a 3-stair jump. So now we would actually have f of 7 equals f of 4 plus f of 5, f of 4 plus f of 5 plus f of 6. Why? Because on the last step, he can take a 3-stair hop. So we can reach the 4th step in f of 4 ways, right? And then from the 4th stair, he can take a 3-step hop. That's one way. Also, he can reach the 5th stair and then take a 2-step jump. That's f of 5 ways to reach the 5th chair and take a 2-step jump. Or reach the 6th stair and then take a 1-step jump. Because we're on the last step, which means the last jump, he's allowed to climb 3 stairs. So he can just directly go from 4 to 7 because it's the last step. So we also have to add f of 4 here. And that becomes 5 plus 8 plus 13 equals 26. So 26 is our answer. Let's summarize real quick. Okay, so the idea was, let's try some small values first. And we saw that these values are pretty easy to do manually, you know? 7 on the other hand, So we decided, let's see if we can make big values in terms of smaller values. Fourth stair, we decided to go from the third or the second stair. And that gave us f of 4 is 5. And then we were able to derive a general formula by using the same reasoning. And then from there, we could just iteratively plug in previous values to get new values. So it was like we made a super complicated big problem into just a few small problems. And that is the powerfulness of recursion. It's so amazing technique, such an amazing technique to use for competitions. Not all recursions are going to be in terms of number of ways. Sometimes there's a probability recursion, and let's explore that. A cricket randomly hops between 4 leaves. On each turn, hopping to one of the other 3 leaves with equal probability. After 4 hops, what's the probability? The cricket returned to the original leaf, the leaf where it started. 4 leaves. Okay. Let's say A, B, B, P. So you might be wondering, A, B, 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 why did you do that? So A is the original leaf, and B, all of these 3 leaves are the other 3 leaves, and I'm going to call them all B. You'll see why in just a second. What is the probability after 4 hops? So one way to do this is to use casework, and that does work, but it's a little bit tedious. So let's try recursion, this time with probabilities. Okay, first of all, let's try and construct a recursion. So let's say, in this case, we'll actually decide to have 2 recursions. Let's say that A of n is the probability of being on the lily pad labeled A. Remember, this is the original lily pad, original leaf. And let's say A of n is the probability that we're at the original leaf after n hops. Let me write that down. Probability on leaf A after n hops. Similarly, let's say B of n is a probability and on any of the B leaves. So not just one of the B leaves, on all 3 other leaves. So on any leaf B after n hops. So now we've defined 2 functions, and now this part is to write a recursive equation. Okay, let's try and find one for A of n. And the idea here is we can write an recursive equation between each other. And let's see what that means. So A of n. What's the probability will be on leaf A after n hops? So recursion is kind of like, to see this, you need to look at the previous cases for n minus 1 hops. So directly looking at n hops and trying to construct from 0, basically the idea is, because probability after n hops, we look at the ways it can reach A after n hops. So how can it reach A after n hops? Well, the only way to reach A is from a B leaf, right? From a B leaf, it must jump to A. So for it to be on leaf A after n moves, it has to be on a B leaf after n minus 1 moves, right? Because it says it will hop to one of the other 3 leaves with equal probability. Right here, it says that it will hop to one of the other 3 leaves with equal probability. So you can't hop from A to A. That's just not how it works. So to hop to A, we must originally be on B after n minus 1 moves. Now, if we were on leaf B after n minus 1 moves, what's the probability we'll be on leaf A? Right here it says one of the other 3 leaves with equal probability. So on B, all these 3 leaves, it will go to any of these three leaves with equal probability. There's three different leaves, and only one of them is an A. So a 1/3 chance. So if the leaf is on A after n-1 moves, there's a 1/3 chance it will be on, or if it is on B after n-1 moves, 1/3 chance it will be on A after n hops. And like I mentioned earlier, if the cricket is on A after n-1, there's no way it can go to A after n moves or n hops, because you can't go from A to A. It says one of the other three leaves. So we can just cross that out. It's basically nothing. It's nothing, right? Now, what about B of n? We can write a similar recursion. B of n. So B of n is a little bit more involved. So how can you reach a B lily pad after n moves? So the idea here is that the B has different possibilities. Let's say that we were on a lily pad after n-1 move, or a leaf. I keep saying lily pad. If we're on a leaf after n-1 moves, then there's a guarantee we're going to go to B. 1 chance, or 3 out of 3 chance, however you like it. So let's just say 3 out of 3, right? Because A has 3 choices, all of them are B. So if the cricket is on A after n-1 moves, it's guaranteed to be on B on the next move. So it's just 1, right? Now, what if it's on B after n-1 moves? Can it go back to B after n moves? Well, let's say it's on this lily pad after n-1 moves. It has 3 choices. 3 choices, right? 2 of them are B, 1 of them is A. So 2/3 chance of going to a B lily pad. If the cricket is originally on a B lily pad, there's a 2/3 chance it will go to another B lily pad. So we get this equation over here. So now we have 2 recursions. Now we should just be able to solve. So for this type, let's make a table. So let's say number of hops, 0, 1, 2, 3, 4, right? And let's see that this is A of n and B of n. So what is A of n after 0 hops? What's the probability of being on the original lily pad after 0 hops? That's just 1, of course, right? You start at A, so the probability of being on an A lily pad after 0 hops is just 1. And that means the probability of being on another lily pad is 0, of course. Okay, now A of 1. Now we can use our recursion. A of 1, right, from this is 1/3 B of 0 by our recursion. B of 0 is, well, it's just 0. So this is simply 0. Now, what about B of 1? Let's write that in our table. So now we could plug it into this complicated looking recursion, but there's a very clever trick you can use here. Notice that the sum of probabilities is always 1, right? The sum of the probability the cricket is on A and the cricket is on any of the B lily pads is 1, right? The total probability is 1. So what that means is that A of n plus B of n is always 1. The probability of being on any lily pad after n hops is 1. So instead of plugging it into this recursion, we can just do 1 minus A of n. And in this case, that's 1. And that's a really nice trick. So we don't even have to do any complicated recursion putting stuff. Although if you did do that, it would still give you the right answer, just a tad bit harder. Okay, A of 2. A of 2 is 1/3 B of 1. And B of 1 is just 1, so just a third. And again, we don't have to plug it into the scary recursion. 1 minus a third, 2/3. Okay, A of 3 is just 1/3 B of 2. And B of 2 is, well, 2/3. So 1/3 times 2/3, that's 2/9. A of 3 is 2/9. And again, 1 minus 2/9, that's 7/9. So that's B of 3 is 7/9. A of 4 is just 1/3 B of 3, and that's 7/27. But notice what the problem asks. It asks, what's the probability that cricket has returned to the leaf where it started after 4 hops? So what's the probability it will be on leaf A after 4 hops? That's A of 4. Well, we don't even have to calculate this. Our answer is just 7/27. Really cool. So the solution. Let's quickly recap. So we defined A of n to be the probability it will be on the original leaf after n hops, and B of n on any other leaf after n hops. And then we came up with this recursion by considering the different cases. So we considered the different ways we can get to A after n hops. And we found that you can only get to A from a B leaf if the cricket is on a B leaf after n minus 1 hops. And even then, there's a 1/3 chance. So we came up with this. And for B, we also came up with the recursion by similar methods, but we didn't end up using it. And then we constructed a table and just plugged in the values and iteratively calculated them, and we kept in mind that A of n plus B of n is 1. The total probability of being on any leaf after n hops is just 1. And that's how we got our answer. Okay, that was a cool problem, but now we're ready to move on to algebra. Now, algebra is one of the most common topics on the AMCA, and we'll be exploring how to solve some non-standard and interesting algebra problems that are not found in school math in the next video. You can click on it right there.